Hello, everyone. Today I'll be presenting the paper. It's a very long title, but what we essentially do is we verify knowledge approximations that you do in like quantitative information flow, and we use that for declassification purposes. But I'll walk you through what each of these terms mean. So, as we all know, information leaks are really common. I mean, from dating apps all the way to the ad industry, Google, Facebook, you name it, all have leaked your private information, and it's really common. So, as a research community, we have indeed come up with techniques that called information flow control, which enforce a formal property called non-interference. And really, what that means is any computation on a secret input should not influence a public output, right? And this is great. It allows us to prove like really secure systems. But when you apply that to a bunch of real use cases, it turns out to be a too strong property. So as an example, imagine like you have a password that's a secret. You want to check the password, and then eventually you want to log in the user or not. And that's a public operation, right? So, or like you have a user location and you want to show an ad, but showing the ad itself is a public operation. And this last step of showing the result to the public breaks down non-interference. So what we have come up with as a technique, like not we, as a community, there's this idea of using declassification. So declassification looks something like at the selective points, you allow non-interference to weaken, which means you are really saying like, trust the programmer here, they know what they're doing. So but if the programmer makes a mistake, that means they'll leak more information that they intended to, and that's bad. So now this work sort of wants to put guardrails on that, and there are two key components on getting there, right? So in the computation step, the first thing that you need to do is estimate how much knowledge an adversary can learn about the computation from the results. And once you have some estimations and you can walk through the prior knowledge of the adversary and the posterior knowledge of the adversary, then you want some mechanism to enforce certain policies that bound these information leaks, right? Coming to our contributions, we do three things. First, we have a verified quantification of this adversary knowledge. Then we automatically synthesize a function that computes how the knowledge evolves, so computes the posterior of the knowledge in some sense. And we also enforce, give you primitives that allow you to apply policies and safely declassify the results of the operation. So I'll walk you through an example of how this turns out. So imagine there's a user who's hungry, and they're like scrolling through their Facebook app, and there's a restaurant, and let's call this restaurant Pizza Hut because it's a malicious restaurant. It really wants you to it wants to find out your location and not serve you food. So what they'll do is they'll start off by making an assumption that the user could be anywhere in the gray area, right? So we call this gray area the prior knowledge of the restaurant, right? Now the key question here is, can the restaurant make enough queries about your location so that they eventually narrow down the user? What do I mean by queries? I mean something like this. A query can be something like, if the user is nearby the restaurant, show them the ad. And in this case, what we are doing is we are checking if the user is within 100 units of Manhattan distance from the restaurant. Then the user will be shown the ad. Even though the nearby query returns true, just by looking at the result of the query, let's say if it's true, you know that the user is within this blue diamond, or if not, then it's in this gray area, right? So by looking at this response, the restaurant can learn where the user is. And formally, how this is done is the restaurant started off with this gray rectangle that I showed, and the region that the nearby query encloses, you intersect those two regions, and that's how you get that. Now, the same restaurant has a different location because it's a chain, and now it's sending out another query by changing the location. Let's say now this new location is like 400, 200, And since the restaurant already evolved the knowledge to this blue diamond, now running this new query nearby 2, which is checking for 400, 200 locations closeness, you can see if you intersect those two knowledge, it's very clear the user is very in the tiny diamond, right? And that is probably what you never intended to do. Like you never wanted to reveal the user's precise location in the first place. So we did this in 2 queries, but you can imagine like you can do multiple queries over time and change the queries and eventually get to a lower, like very narrow precision of the user's location, right? So we saw the problem and we want to write policies to prevent these problems, right? So if you look at the blue region, it represents like multiple secrets. And by secret, I mean this user location. The user could be anywhere in this blue region. So what we want to do is we want to reason over sets of secrets because we want to reason over this blue, like these regions. And we represent this set of secrets as abstract domains, which is shown by the ADOM type here. But what these policies are really is it's predicate on those abstract domains. So if the predicate is true, then your result is declassified. If the predicate is false, then you have a policy violation. And the primitive that ANOSY provides is this downgrade statement, which takes the secret and then the query, and then it, if it's safe with respect to the policy, it returns the response. So in the first case that I showed before, if the first query will be declassified correctly, so you get true. The second query, you get down to a very narrow location, and that's not allowed by the policy, so you get an error, right? Now, what we did in this previous example is this nearby query split the region into 2 halves. So one is for the true response, which is the blue diamond shaded region, and one is called the false area, which is like the green shaded region. Now, any point in this yellow or green region is indistinguishable to the attacker because all points in this green region evaluate to false, and all points in this yellow region evaluate to true. So the attacker does not know exactly what these individual points are when they know the response. So we call these green or the yellow sets indistinguishable sets. Now, how do we evolve this knowledge? As I showed before, like we have a prior, and then we have this region that we derive from the query, and we take this intersection, and as like we get more and like that's how we compute the posterior, and that's exactly what happens. So if you intersect the prior and this diamond, you get, depending on the query's response, you get 2 outcomes, right? Now let's assume like for this query, the first this query evaluates to true, and this becomes the new prior because like the restaurant has learned that the user is in this diamond. So this is now the new prior. Now, again, the new malicious query comes in, which is like the 400, 200 locations query. This is again intersecting. Now, looking via the indistinguishable sets again, if you intersect those, you'll get 2 possible outcomes again, the false and the true outcomes. And if you look at this, this is like reasoning over this, like shapes are becoming very tricky. And by the way, these 2 shapes at the bottom are not to scale. The true shape is like this tiny intersected region from in the middle. The false one is this kind of Apple logo without even if it was a rectangle. But the way this works out is because the restaurant already knew that the user was in this yellow region. By execution of the second query, they learned that the user is not in this intersected region. They'll like narrow down their posterior, right? So this is how the tracking knowledge evolves. But it turns out like as you do more and more queries, you realize that you cannot do reasoning over these arbitrary shapes, and you get more and more tricky shapes after this. So what we want to do is we want to approximate these queries, these shapes. And in this example, we do under approximations with, let's say, intervals, which in the 2-dimensional space map out to rectangles. And the green overlays that I'm showing on this top are like the under approximations are one possible under approximation. But you can imagine like doing different kinds of under approximation. Now, if you look at this, coming up with this under approximation is what makes like all of these, like this mechanism work. But if you make a mistake, it means you can have security bugs. So ANOSY automates this, and it also verifies this. The way we represent these abstract domains and approximations is we encode them in a refinement type. The refinement type takes as a type parameter this lambda, which says any point in that domain should satisfy this property. So with our example, this would mean that any point in this gray region should satisfy the nearby query, right? And in our work, we instantiated ADOM with intervals or power set of intervals. So you define the value for the type, and then automatically it can be checked by liquid Haskell if those indistinguishable sets are correct or not. And now we mentioned before, like there are like two possible indistinguishable set. One for the true response, one for the false response. And if you look at the refinement types, the predicates sort of specify that. The first refinement type says any point inside is nearby, and the second refinement type says any point inside is not nearby for the false indistinguishable set. Now, if you think about it, like those numbers are very tricky to come up with. If you make a mistake, it's very hard like to find out what went wrong. And we can take that burden off the user as well. We can just leave that a hole. And since we have the right constraints from the refinement types, we can just offload that to the solver. We can say, give me a domain that satisfies this predicate, and that domain should be of a maximum size. And indeed, Z3 comes out with the correct solutions here as well. Now, I mentioned we have so all you need to do is intersect this indistinguishable set with the prior knowledge. Now, and this knowledge is used by the downgrade operation. Now, this is the key contribution of ANOSY, because right now you don't need to run abstract interpretation for each declassification query. Instead, you do this intersection, which means it's almost a zero-cost operation and much faster at runtime. And so we verify all those claims that we made. We do that with a few problems that existed in the literature before, and these problems have secrets ranging in 2 all the way to 4 dimensions. And we evaluate these with intervals or power set of intervals. Our synthesis times are reasonable, but it's a compile time cost, which means you pay that cost once, but on the runtime it's almost zero cost. Whereas existing tools like Prob, you have to run the abstract interpretation over and over again. So asymptotically we're faster, but there's an upfront compile time cost. But our power set estimation algorithm turns out to be better than existing tools. So we get much higher accuracy compared to tools like Prob. And this turns out to help us mostly in the case of conditionals, when conditionals are present in the query. Now, another experiment that we did is, if our tool works as expected, then as we increase the power set size of the power set of the query, we should be able to answer more and more queries and declassify them, right? And that's indeed what we did. We randomly generate queries, and we keep on trying with higher and higher power sets with the expectation that more queries should be answered. And indeed, that is what happens. If you look with one interval in the power set, we kind of stop answering at 8 queries maximum. Whereas if you have 10 intervals in the power set, we go all the way up to 15 queries answered. So as expected, it's working and allowing us to answer more queries. So in summary, what we have is a verified approximation of attacker knowledge, and we verify this using refinement types. We have an SMT-based optimization, and the downgrade is implemented as an ANOSY monad. And we did not discuss this in this talk, but the details are in the paper. And the ANOSY monad allows us to layer this over other monads like LIO, which means it can enforce non-interference correctly. Also, we synthesize more precise posteriors that are almost zero cost at runtime. The code is available open source at this URL. Thank you.
Okay, let's thank the speaker. Okay, so I have a quick question. Could you briefly comment about the expressiveness of your predicate languages? in the sense that what are some, in the real example, what are some properties that probably go beyond the scope of your current prefix language, or it might lead to some undecidable fragment that might like cause trouble to the constraint solver. Thank you.
So the kind of queries we're doing right now is like totally restrictable in the predicate language. So we do not support recursion as of yet right now, and loops as well. But everything else should work out fine as long as it's representable in this quantifier linear integer arithmetic fragment.
Hi, Andrew Myers from Cornell. So this is very interesting. I think work on giving us a better handle on downgrading is really interesting to work on. One thing I think I probably don't quite understand what's going on here, but in the original program you had true and false, and then you observed that sometimes those two answers could give you more information than you really wanted to give. Now you have your system is now generating true, false, or error, it seems to
me. Yeah. So like you get the right response or error. Yeah.
But isn't the error itself also releasing information? Like, are you actually better off, I guess?
It does indeed release more information, and there's no way we can get around that because like we have to stop answering queries. But like anything we reveal after that will reveal some information that we're violating a policy, but that sort of reveals more information about the policy itself, not the secret.
I see. Okay, great. Thank you.
Yeah, thank you for the talk. My question is whether you handle other things other than kind of, it seems like your examples are mostly focused on like real numbers or coordinate spaces. Does this work also apply to kind of discrete domains or discrete types?
So in our examples, we had discrete things like sort of conjunction, disjunction, and other things as well. If checking if something is equal to true, false, but true, false like translate to 0, 1 in the integer space, which is why it works out nicely.
Okay, so any last questions from the audience? Okay, so you mentioned this malicious restaurant at the very beginning. So I was wondering if I take an existing code base, which essentially leak or like have problem like that violate the policy, how difficult is that to repurpose your system to say like automatically fix that in a way that it conforms with the policy?
So what my tool like implementation wise expects is you expects the query in a file and it expects some annotation. It will synthesize the posteriors generating function that I showed before automatically. Once those are synthesized, you write your code as you would you do the declassification and use that as you would, and like the synthesized components are there for you to use in an end-to-end system.
I see. Okay, so let's thank her again. Thanks for the great talk. Thank you.